In this video, we are going to be discussing question 6.20. In case you have your old textbooks, it's 7.20. Um, so this question is also related to the stepwise calculation of pH using for weak acids. So I did discuss how to use that stepwise approach in another question. Definitely check that out. I believe I did that for 6.18. Do check that out. In this one, we're just going to be talking through how to solve this particular problem. So calculate the pH of 0.08 molar solution of hypochlorous acid, which is HOCl. The ionization constant is 2.5 into 10 to the power minus 5. Determine the percent dissociation of HOCl. So we need to determine the percentage of dissociated um, of HOCl, and we need to calculate the pH. So let's write down what's been given to us. So we've been given the initial concentration. So I'm just going to say HOCl initial is 0.08 molar. We've been given that the ionization constant is, which is represented by Ka, is equal to 2.5 into 10 to the power minus 5. Okay, now we need to figure out these things. We need to figure out the percentage dissociation of HOCl, and we also need to figure out the pH. Okay, so these are the two things we have to figure out from this particular for this particular question. Okay, so first of all, let's write down the equation. So HOCl plus H2O is in equilibrium with H3O plus ClO minus. Okay, so this is the equation, right? Now, the first step we need to do is write down the things in a tabular form. Okay, so first we start with the initial concentration. So the initial concentration is 0.08 molar for HOCl. For the other things, it is 0. Okay, the second thing we do is write the change. How much is the change? So change to reach equilibrium, let's assume that this concentration goes down by X. Okay, whereas this one goes up by X, so does this. Okay, so we're assuming there is an increase in concentration by X for these two, and then this one there is a decrease by X for HOCl. So at equilibrium, the concentration is going to be 0.08 minus X, and then for this it'll be X and X respectively. Okay, so we first wrote down all of the initial change and the equilibrium concentration in a tabular form. So the next step is we are going to calculate the value of Ka. So we've been given the value of Ka, but according to the equation, the Ka's formula is going to be H3O plus concentration into the concentration of ClO minus divided by the concentration of HOCl. Okay, so this is equal to X into X divided by 0.08 minus X. Okay, so this is equal to X square divided by 0.08 minus X, which is equal to 2.5 into 10 to the power minus 5. That is because we've been given that the value of Ka is equal to 2.5 into 10 to the power minus 5. Now, the value of X is at this place is especially less significant, or let me just mark it with another ink. So the value of this X is not very significant. And the reason is because the initial concentration, in comparison to the initial concentration of HOCl, which is 0.08, the amount that is dissociated is significantly less. This is because, first of all, HOCl is a weak acid. Okay, HOCl is a weak acid, which means it won't undergo dissociation to a great extent. And if you notice, the value of Ka for this particular for this particular question is 2.5 into 10 to the power minus 5, which is significantly small. Okay, so this in turn, if you remember, we discussed that the value of Ka also gives us the information of the strength of the acid. So a strong acid usually has a higher Ka value, whereas a weak acid has a low value of Ka. So what we have over here for the value of Ka is basically 2.5, right? So 1, 2, 3, 4, and 5. So it is 0.00, wait, 0.00025. So this is how dilute the this is how low the value of Ka is. So this also gives us the information on the fact that HOCl is a weak acid. You don't actually have to memorize. So that's a point that we're deducing from the fact that Ka is significantly low. So what we're going to do is we are going to ignore this value of X. Okay, we're ignoring that value for just the denominator. So you'll be left with X square divided by 0.08 is equal to 2.5 into 10 to the power minus 5. Okay, so what we can do is, what we are going to do is simplify this, obviously. So X square is equal to 2.5 into 0.08 into 10 to the power minus 5. Okay, so this is equal to X square is equal to 0.2 into 10 to the power minus 5. Okay, so you can also say X square equal to 2 into 10 to the power minus 6. The reason I did that is because we can just shift this and we're going to take a square root on both sides. So you'll be left with X is equal to root over 2 into 10 to the power minus 3, because root over 10 to the power minus 6 is 10 to the power minus 3. So X will be equal to 1.41 into 10 to the power minus 3. So this is the value of X. Now, the percentage dissociation for HOCl will essentially be the percentage will be equal to the concentration of HOCl, which is the dissociated one, divided by the or the initial concentration. So HOCl initial into 100. Okay, so basically you have the dissociated concentration of HOCl is essentially 1.41 into 10 to the power minus 3, because that's the concentration of H3O plus and ClO minus, right? So that is the dissociated concentration. So you have 1.41 into 10 to the power minus 3 to the divided by um, 0.08, which is the initial concentration, into 100. Okay, so essentially you will be left with 10 to the 1.41 divided by 0.08 into 10 to the power minus 1, because 0, 0, this becomes minus 1. Okay, so this further on simplification gives us 17.625 into 10 to the power minus 1, which is equal to 1.7625%. So the percentage dissociation is just 1.7625. So what we did was we just used the dissociated divided by the initial concentration to get to the percentage value. The last one we need to do is figure out the pH. pH is going to be equal to the value of minus log concentration of H plus. So minus log 1.41 into 10 to the power minus 3. So it will be minus log 1.41. Also, if you find it, um, plus, I'm sorry, got distracted talking to you. But if you find it easy to try and solve it, definitely pause the video at some point and then like solve it. I know it's the end of the question. I should have told you this before, but you can also follow along. So log for 1.41 is 0.1492 minus 3, and this is equal to minus of minus 2.8508, which is equal to 2.850. So minus into minus is plus. So all we did was we used the we figured out the equation, and this is very important. You need the tabular form to actually be able to calculate the value of the concentration of H3O plus, and then we were able to calculate the concentration of H3O plus, and also we ignored this X because it's a weak acid. If you notice, the value of Ka is also super low, which implies it's a weak acid. We then use the percentage dissociation formula, which is HOCl dissociated divided by the initial concentration of HOCl into 100, and then simplified it to get the percentage dissociation, and then the pH will be minus log concentration of H plus, and that's I'm assuming at this point you know how to do that. And with that, we're done with 6.20. In the next video, we will be discussing the ionization of weak acids. Oh, weak bases. I'm sorry. We just finished weak acids. It's weak bases.